Hi, good morning or good evening, everyone, depending on your time zone. Great to see many of you here. Okay, let's wait for one more minute before we get started. Let's see. Okay, I think we should get started. And okay, people are still coming in. So I know this is the weekend, right? And at WashU, if you're at WashU, there was a fantastic event organized by Elliott Society, right in front of the tower, in the Tisch Park. And today, as many of you know, is the hot balloon launching day. And if you are close to Forest Park, you probably would see many hot balloons fly over your building. So it's a once-a-year event. And they had the hot balloon glow last night, and today is the launching time. Okay, so I don't know whether the event is still going on or it's over, but no, every year at about this time, they will have this hot balloon event. Many people from other states drove their hot balloon and join the festival and competition. This was a fantastic event. If you have never been to that event, I would highly encourage you to join next year. Okay, so let's get started today. And I know a few people got sick and told me, and especially Fun, she was supposed to give the presentation, but no, she got sick. So I told her to rest a while, and then I'll do a presentation instead. Okay. And we do have some new people. So that's probably do a quick round of self-introduction. I know, we've been doing introduction all the time, but I think that's needed because we always have some new participants. So let's do a quick round of self-introduction, just your name and your program, or anything you want us to know about you. And then we can start the presentation. Okay, so we'll just go around the Hollywood Square. So each of you can just briefly introduce yourself. You do want to get started?
Sure.
Hi,
Hi.
Professor Ang.
Oh,
Yeah, sorry, I probably didn't pronounce your name right. So maybe Yu, you want to talk first, and then Jing, right?
I'm sorry. I'm Yu Yang. I'm a first-year PhD student in computational and data sciences. So nice to meet you all.
Great. And Jing.
Hi, Professor Ang. Could you hear me?
Yeah, we can hear you.
Okay, thanks. So glad to meet you all via Zoom. And I'm a biostatistics student in medical school, and I'm so interested in artificial intelligence. And also it's my first year to come to St. Louis. Yeah, so I hope to have a good time with you all and learn something from you all. Thanks.
That's fantastic. You are most welcome, Jingyi. And Peiqi.
Hello, everyone. My name is Peiqi. I'm a information system management student in engineering school, but due to the interest, I get in touch with Professor An, and we have worked with a couple projects together, and I learn a lot about artificial intelligence, especially about the code interpreter. And well, it changed the name actually. It changed to advanced data analytics. Really interesting. But anyway, so nice to see you guys, and welcome.
Great, wonderful. And Helen.
Yeah, thank you, Professor An. Hi, everyone. I'm Helen Etiale. I'm a first-year PhD student in the Public Health Sciences track at Brown School. Yeah, so I don't have much knowledge of AI, but I'm just really interested in trying to gain that knowledge. So I thought I'll join this group to be able to do that. So thank you for having me.
Wonderful. You're most welcome. Passion is all we need. And Chen.
Hi, all. My name is Chen. I'm the third year MSW and PhD student, and good to see you all.
Great, great. And Jiahe.
Hi everyone, my name is Jiahe. I'm from the University of Melbourne at Australia, and I joined Dr. N's AI and Health Data program this year. I'm really happy to join this AI interest group and learn from all of you guys. Thanks.
That's great. So Jiahe, what time in your local time? What time is that?
It's 10 a.m. Sunday in the morning.
Oh, okay, great. Wonderful. Charles. Well, we can't really hear you well.
Yeah. Hi everyone. I'm Charles. I'm a second year DCDS PhD student. Glad to meet everyone today.
Great, wonderful. And Bob.
Hello, everyone. Can you hear me now?
Yeah, we can all hear you.
Great. Hi, everyone. I'm Bob Cormier. I'm actually not a student anymore. I got my PhD in neuroscience many years ago, and I'm currently a behavior analyst. I work with the Department of Mental Health for the state of Missouri. And my interest in joining this group is to learn more about machine learning and its application to data analysis.
That's fantastic, Bob. You are most welcome. And Xiaoxin.
Hi everyone, I'm Qiuxin Wang. I'm a PhD student in China. This is my last year of my PhD, and now I am a visiting scholar of Dr. An.
Wonderful. And Shanshan.
Hi everyone, I'm Shanshan. I'm fourth year PhD student in epidemiology. I'm from UNT Health Science Center. I had two papers with Dr. An so far. I'm glad I have this opportunity. Glad to see you all.
Great, yeah, wonderful. And Jin.
Hi everyone, my name is Jen. This is my second year here. And right now I'm a student in MSW program, but last year when I came here, I studied as a student in MSP program. So welcome to our group.
Great. Meng.
Hi everyone, my name is Menmen Ji. I'm currently a postdoc working at WashU School of Medicine. I was the PhD student of Dr. N, and I have worked as the TA for his AI class in last year.
Yeah, you look tired today. Are you okay? Everything is fine?
Yeah, I have a proposal due. Right.
Okay, good luck. And Jeremy.
Hi everyone, I'm Jeremy. I'm a senior student majoring in math and CS, and I'm really interested in AI and its applications and looking to study that in grad school. So that's why I joined this group.
That's fantastic. You're most welcome. And Xi.
Hello. Hello, everyone. My name is Xi Wang. I'm second year and PhD student. I'm quite interested in machine learning and deep learning studies. Very happy to learn with you all. Thank you.
Okay, great. So I guess everyone has introduced yourself. If anyone is left, I apologize and just unmute and speak. Anyone? Okay, so probably we covered everyone. That's fantastic. Okay, so let's get started. And well, I have to apologize though. I just prepared this presentation in a few hours because it was all in a hurry. So if there's anything that doesn't make sense or you want further clarification, just let me know. And I saw that Shambhavi is there. Shambhavi, we just finished a round of self-introduction. Do you want to briefly introduce yourself?
Sure, Professor. Hi, everybody. I'm Shambhavi. I am in the MPH Epi Bio concentration at Brown School, and I use she, her pronouns. Is there anything else, Professor, I need to yeah?
Not really, not really. So because we have new people joining us, so we just want everyone to know everyone else. So that's fantastic. Okay.
Thank you.
Great, thank you. Okay, so let me just share my screen. If you have any question, either unmute or speak, or just post it on the chat, and we will address your question. So let me share my screen. So this is really not presentation slide, but I recently try to use a new type of presentation. It's called Sway. I guess some of you might have used that before. It's a online platform hosted by Microsoft to deliver talk or presentation. So let's see how well it goes. Is very flexible because this HTML file, and automatically formatted. So it should fit into most of the screens, but in case you miss something, just let me know. Okay. So the reason why I bring this topic is because the AI causal inference is a really hot topic nowadays. So just starting from possibly a year ago, there were about 2 or 3 papers on AI causal inference published every single day. So the development of this AI subfield is accelerated dramatically over the past few years. So previously, we learned most of the machine and deep learning through association or associative relationships. Basically, we want to make as accurate prediction as possible, but we don't really pay much attention to whether it is a spurious association or it is a causal relationship. But really, if we do want to understand whether A causes B or why B is caused by A, if we want to understand those causal relationship, we have to dig a lot deeper into the theory of causality and see how AI can facilitate that kind of investigation. So most of the learning, the machine and deep learning you learned so far from my course or from other courses are pertaining to association. Okay, so we'll give you some examples why that is the case and how that differ from the causality that we are going to introduce today. Okay, so well, the AI causal inference is a huge field nowadays, and no one can cover all of them. And the new discoveries on a daily basis. So in this very short time, we just possibly introduce you what is causality, why that differ from association, and give you some hands-on exercises using the Python code to hopefully decipher some of the complications. I apologize, my dog is barking. So that is one thing I have no control over. But well, hopefully you can all hear me well. Okay, so let's get started. So first, let's go back into the history and philosophy to talk about the causes, right? What are the causes of things? Many of you probably know Aristotle, the Greek philosopher, and he described 4 causes. The first one is called material cause. For example, if you see a statue and the material cause would be the marble or the bronze from which it's carved. So that is the material cause, very easy to understand. And the second type of cause is called formal cause. Formal cause means some kind of design or pattern or architecture of the statue, basically the blueprint based on which the statue is made. And the third type of cause is called efficient cause, meaning the process, how something is being made. For example, you must have a sculptor to carve out the stone or the bronze in order to create that statue. So the sculpture work would be the efficient cause of the statue. And finally is the final cause. Final cause means the fundamental purpose, why a statue is created. Maybe that is for honoring some saint, maybe commemorate a historical event, or maybe just beautify a scene, right? So those are the final causes for the statue being made. So that is Aristotle's philosophy regarding 4 causes. Okay. And then the more modern causality theory was actually developed in the 18th century by a Scottish philosopher, David Hume. So David mentioned an interesting observation regarding causality, and his idea can be summarized into 3 sentences. The first one is, we only observe how the movement or appearance of an object A precede the movement or appearance of object B. We know what comes first, what comes next, but we can't really tell for sure that A causes B, right? Because, well, no, A won't have to be a cause of B in order to happen before B. And second is, if we experience a succession a sufficient number of times, we'll probably develop a feeling of expectation. For example, every time we see A and then we see B, for example, every time you see a lightning and after a few seconds followed by the thunder, then you probably form a hypothesis that the lightning causes the thunder, right? Because you observe this many, many times. And every time it just confirm with your expectation. Okay? So the third is, this feeling expectation is an essence of a concept of causality. So basically, Hume's theory is that causality is purely observational and based on strong assumptions, right? Based on co-occurrence of the event, something happened first and followed by the next, but you may never have a formal proof that something happened first is the cause of something happened later. So the machine learning, as we said, most likely work on associations, okay? Because in the machine learning, we try to make some prediction of the outcome based on some features, right? And those features are sometimes representative or suggestive of the outcome. But seldom we ask a deeper question of whether those features causes the outcome, right? For example, if we try to predict the image of an apple, we observe that, well, the texture of the apple, the color would be often either red or yellow or greenish. And based on those features of the color and texture, and also probably the shape, we would make that prediction, right? But we would not say that the color or the shape determine the apple or the other causes of the apple, right? So on the other hand, if we consider how actually human beings form the idea of causality, we could actually trace back to our own childhood if we ever remember, or if you don't remember, no worries, you can just observe how the babies interact with this world, right? So if you observe the baby for a while, you often associate some kind of baby's behavior as being like rude or destructive or aggressive, right? Because some babies may throw things away, may bite something that he or she should not bite, or may be violent sometimes while trying to smash something to the ground or throw things to someone else, or shouting, biting, right? But really, the scientist observing baby's behavior try to understand why the baby behaved like that. And some scientists believe that the baby actually using those behavior as a way to explore the world. Basically, those are the first encounterings know how the causality was formed in someone's mind. Because when the baby throws some things, the baby want to know what is the consequence, right? What is the limit of that? No, would that object fall to the ground, or would this object go to the roof, right? And baby also try to bite things to know the texture, know how hard it is, or soft, whether it's edible or not, or shouting to understand how his or her voice can travel on the atmosphere. And all of that actually are part of the experimental process of the baby, because baby try to understand the physics of how this world behave, and maybe also the social logical side, the social cycle side of how this world may react to the baby's behavior, right? So those probably demonstrate how our human being try to understand the world by interacting with it and experimenting, doing some experiments to understand how the world works. So why experimenting is important? So actually it is pretty profound, because experiment usually give us more evidence about causality compared to simple observation. So if we don't interact with the world, we just observe with our eyes and with our ears, with our five senses, then we may come to a completely naive understanding of causality. Okay? So that is because of the confounding, basically spurious relationship that exists in multitude in this world. So here we give you an example of a naive example, but probably to some extent it is a real world example. Consider that in the summertime, right, you observe a significant increase in the number of people who are joined in maybe rivers or lakes, right? And at the same time, you observe many people purchasing ice cream. Right? There's a significant increase in ice cream sales in the local vendors, right? And then you may, based on your observation, you don't intervene, right? You just observe this association between the increased number of ice cream sales and also the increased number of drawn this accidents, right? And then you come to a hypothesis that, well, maybe ice cream consumption is dangerous. It leads to no accidents, right? And you may even think about, well, some kind of material in the ice cream, maybe the sugar, make people crazy, right? Or make people less cautious about the danger. And then that increases drowning, the accidents, right? So because you don't intervene, you just observe, there's a positive association between these two, and then you draw a conclusion that ice cream actually causes the increase, the accidents, right? So, but here, well, many of you who have learned biostatistics understand confounding, right? So here on the left-hand side, we have this hypothesis that ice cream consumption causes the accidents, right? So this is called a causal diagram. And in this causal diagram, we have nodes and we have edges, right? Here we have two nodes denoting the ice cream consumption. This is one event, and accident, which is another event. And we use this arrow to denote the direction of causality, right? So here it means we use dashed line, means there could be, but not really a causal impact from ice cream consumption to accident. Okay, so therefore we use the dashed line. So this is going to be the graphic model that we are going to use all the time. So on the right-hand side, you will see actually there is a confounder that is associated with both ice cream consumption as well as the accident, which not surprisingly is the temperature, right? Because in the summertime, people feel hot, so people enjoy water more. And then, of course, that increases the chance of drawn and other accidents. On the other hand, because the temperature is hot, so people tend to consume more ice creams, right? So because we, in the naive case, we do not actually consider the confounding effect of temperature, and then we just observe an increase in ice cream sales and an increase in accidental rate, then no, we would conclude that actually ice cream consumption leads to accidents, right? So therefore, as long as we can control the confounder, here the temperature, then the observed relationship between ice cream and accident would disappear. Okay, so but otherwise we would draw a completely wrong conclusion. Okay, so therefore the confounder play an important role in most observational studies. The studies are confounded because there are probably multiple confounders, either observed or unobserved, that may impact our estimated relationship. So it means that without controlling for the confounder, we probably are at risk of estimating a spurious relationship. Spurious relationship means the relationship doesn't exist, but because of confounding, we identified such relationship. Any question or thoughts? Okay. So basically, confounding is strictly a causal concept, right? If we don't talk about causality, then confounding doesn't exist, because confounding is just a relationship, right? Observed relationship, right? It is the same as an association, right? So we talk about confounding whenever we refer to some kind of causal relationship between A and B. So here is an easy demonstration, right? That's make it more little abstract. Now we consider that A and C actually are causally independent. Basically, there's no relationship between A and C. Okay. But, well, unfortunately, B serves as the confounder. B causes both A and C, as you can see here. Okay. A and C are independent. There's no whatever association, but B is positively related to A, and also B is causally related to C. Okay. So in this case, as you can see here, A and B are positively correlated. B and C are also correlated related. But then what happened is that if you plot between A and C, you will see clearly there's a positive association between A and C, although in fact, A and C are not related at all. Okay. So let me quickly illustrate that idea. Let me stop share. Let me, where is that? Okay, so probably here, let me open up this. Hold a second. I'm looking at here. Let me stop share and share again. Okay. So here, let's quickly illustrate this idea. I'm opening the Google Colab, and I'm going to illustrate the idea of confounding. So here we are doing a tiny experiment, right? So we create a random variable B. Okay, as you can see, B is follow a random distribution. Okay, it's a continuous random variable taking the value from between 0 and 1, and is follow a uniform distribution, and we are going to draw 100 samples for B, and then we create this A and C. Okay, so A and C, as you can see here, A and C are causally independent from each other, right? A and C are not related. B causes A, okay, and B causes C, but A and C have no whatever relationship, right? So by design, okay. And then we can check the Pearson's correlation coefficient between A and C, okay, and let's see here. Wow, actually A and C here, they are very strongly correlated with a correlation coefficient of 0.96, almost a perfect positive linear correlation, right? And why is that? Okay. That is because there's a confounder here you did not control for, which is B, right? Because B is a common cause of A and C. So in this case, although A and C have no whatever relationship, but because you do not control for B, then there's a spurious relationship, a very strong spurious relationship, right? So here I create I create the some figure for you to take a look. So here we see a not surprisingly A and B and B and C, they are all positive correlated because this is by design. But then what is unfortunate is because you don't know the existence of B, or you fail to control B, in this case, you would draw a wrong conclusion that A and C are positive correlated. Or you may even say, well, B is a cause of C, A is a cause of C, or C is a cause of A, right? Which is completely wrong. Okay, let me stop share. Any questions so far? Anything that doesn't make sense?
Professor, can you elaborate on the first code about the random seed for reproducibility? I mean,
oh, okay, yeah, sure. So let me share it again. Yeah, so yeah, because we focus on the larger picture, so we don't really talk about the details. But here, yeah, the random seed is just for reproducibility, because if you do not set a seed, so every time you run the code, you are going to generate new numbers. Okay, if you set a seed, the random number generator going to produce exactly the same number every single time when you run the code. Okay, so that is a common way that in Python and in machine learning that we try to increase the reproducibility of the results.
Okay, thank you, Professor.
Sure. Okay, great question. Let me stop share. And any other questions? Okay, so hopefully I convinced you that confounding is an important thing that we need to consider, especially on your observational studies, right? Okay, so let's go back to the where is my, oh, here. Okay, let me share. Okay. And then we can consider no other cases. For example, a marketer's dilemma. That say you are a tech-savvy marketer and you want to effectively allocate your direct marketing budget. And then you often ask the question that, well, how am I going to allocate my budget, right? Should I do this way or that way, and which one give me a better or improved ROI, right? So that is the often the question you want to ask. But fundamentally, this marketer's dilemma is a causal inference problem, right? Because you want to tell, in fact, the factual and counterfactual. So here the factual is, well, no, if I, so why here, why I 1 and why I 0, 1 means that you have say strategy 1, right? And 0 means you have strategy 0, right? So if you have 2 strategies, you either allocate say the money to some project or do not allocate money to that project, right? In this case, you want to know if everything remains the same, allocating and not allocating that budget to a project leads to what outcome, right? So you fundamentally want to know whether this is positive or negative and what is the magnitude of that, right? But the problem is that you only observe one of the 2 outcomes because you either allocate the money or not allocate the money to that project, right? You cannot observe in the parallel world what's going to happen with and without allocating the budget, right? So that is the fundamental challenge. And that is a fundamental challenge for any causal inference, because we are asking the question of counterfactual. What would happen if we did not do that, right? So formally, we would say the counterfactual are estimated of how the world would look if we change the value of one or more variables, holding everything else constant, basically holding the entire universe constant, right? Anything else should stay the same, just say the allocation of budget or just the implementation of this treatment, right? So therefore, the fundamental true causal effect tau is unknown. So we would never ever observe the counterfactual. So therefore, we would never ever know the exact value for tau. Okay. Question, comments? So feel free to post if you have questions on the chat. Okay. And now let's illustrate the counterfactual in a more dramatic fashion, right? So here, no, we have this is of course something hypothetical, right? It's not something real. Say we have two drugs, drug A and drug B, to prevent blood clot, right? And of course, no, we want to choose the drug that is more effective in preventing blood clot. So if we observe the data here for drug A and drug B, well, it is a no-brainer that we are going to choose drug B, right? Because drug B, in drug B, 81% of the people did not develop blood clot, whereas 78% of people in drug A did not develop blood clot, right? So therefore, drug B should be preferred, right? But well, no, if I show the data below, you are going to give a second thought, okay? So now the data, the underlying data doesn't change at all. It's still the same data set. But what I did is I stratified the data by gender, okay, by male and female, okay? And let's look at this data again. Okay, the first one to the first few columns doesn't change, but here we added the number of females and number of males in it. If you take a look of the percentage, well, the overall percentage doesn't change. It still tells you the very same story that drug B should be preferred because it has a higher percentage, okay, of people not developing blood clot. But if you take a look of the percentage of male and also percentage of female who did not develop blood clot, you would actually prefer drug A, because for drug A, 70% of female did not develop blood clot in comparison to 6% in drug B. For male, the same story. 93% of the male in drug A did not develop blood clot, whereas only 92.5% of male in drug B did not develop blood clot, right? That is not possible, right? That is because you change the data. Well, no, the answer is no. We did not change the data. The data are still the same. Okay, but you would draw very different conclusion if you stratify by gender, right? But why that's the case? And in this case, which drug should you prefer? Would you prefer drug A or would you prefer drug B, right? So that is the complication of confounding, right? Because based on whether you control for the gender, you may draw different conclusions regarding whether drug A or drug B should be preferred. And think about how many ways you can stratify the sample. You can stratify by gender, you can stratify by age, you can stratify by other chronic condition, etc. Right? So which one should we prefer as the indicator for the effectiveness of the drug? There's no simple answer, right? So that probably just give you some idea of the role of confounding in causal estimation. Any question? Good. Okay, so let me stop here. And then let me open another file. Go back here. Wait, okay. Let me put here. Share again. Okay, so now we learned enough to introduce the ladder of causation. Okay, so the ladder of causation actually was originally, the idea was originated by Judy Pro. So Judy Pro is a famous computer scientist and philosopher. He is an Israeli-American scientist who received the Turing Award, which is the highest award in the computer science field, equivalent to the Nobel Prize to natural sciences, and for his contribution in causal inferences and discovery. So many of the theorems were proved, initiated and proved by Pro. Okay, so based on Pro, his idea, he came up with the idea of the ladder of causation, which I would say is very intuitive. So he claimed that there are, in that ladder, there are three rungs or three levels on the ladder. Okay, the lowest level is association that we already talked about, right? And why association is at lowest level? Because it's subject to confounding, right? Because association, we always say that association does not equal to causation, right? And then association should be at the lowest level, right? And the second rung or level is intervention, right? As we learned in the previous lecture, how the babies experiment with its environment, and the babies are in fact doing interventions, right? Trying to change the condition to see what is the impact on this physical or mental world, right? maybe, you know, if you remember that babies always want to test the limit of their parents, right? We'll know, well, when and to what extent the parents would shout at a baby, right? The parents would be outraged, right? So that is an intervention on the psychosocial side of the world. And the highest rank or level of causation is called counterfactual, right? Intervention doesn't actually give you a good estimate for the counterfactual, and we'll come to that question later. Okay, so basically, the highest level of causation is counterfactual, because if we know the counterfactual and the factual, then we'd be able to estimate precisely tau, right? That we talked about in the previous session, right? But well, in most cases, we can only observe things, so we only estimate the association, and sometimes we can change the world to observe what's going to happen. So that is in the field of intervention. But well, we would never, unless we have a time machine or something, we would never really be able to completely decipher counterfactual. Any question? Okay. So here is a summary of the association. Association means how does observing X change my belief in Y, right? So this is very much in the David Hume's philosophy that observing something happen first and then something happen next give you some feeling about the causal relationship, right? So the intervention is in terms of doing, basically what will happen to Y if I do X, right? What's going to happen to this piece of Lego if the baby throw it to the ground, right? Or towards, you know, some other baby sitting next behind, right? And counterfactual, you know, is imagining, okay? Because, well, no, you will never be able to truly observe counterfactual, right? So maybe there's a chance, maybe, you know, there's alien technology allow you to do that, but it's probably above our understandability. So the question is, if I had done X, what would Y be, right? So that is the fundamental question, is a kind of soul-seeking question every scientist want to know, but may never be known. Any question regarding those three ranks? Okay. And then let's talk about the a example of the drug effectiveness, right? So the drug effectiveness, if you understand from the purely observation perspective, then you may say, well, I maybe have heard that doctors say the drug D help the patients, right? Or if you observe some of your friends recover better after taking medication D, right? So that is RAG 1, right? Because it's purely observation. And the second is intervention, right? Intervention means if you are really skeptical about whether drug D is effective or not, no, you could maybe run a trial, maybe either randomize people into two groups, and one people taking placebo, the other people taking the drug, or you run a pre-post trial observing people before and after taking the drug, right? And then they give you some changes of the outcome, right? So, and then, well, you would say, well, I did some intervention, someone take the drug, and we observe the effect versus those who did not take the drug, and then we compare those two groups, or before and after, so that we would say, well, the drug is effective because it changes people's health outcome, right? So that will be in rank 2, basically doing trials, which are interventions, right? But of course, it is not the same as the counterfactual, because the counterfactual question would be, if compared to me taking the drug, what would be my outcome if I did not take the drug, right? Basically, comparing you and yourself at two parallel world. One take the drug, the other didn't. Okay. So, and now let's talk about conditional probability, because conditional probability is important to understand both the observation as well as the intervention. Okay. So many of you probably have learned the conditional probability. It's a very easy idea. So basically the question is, we use P, X, and then Y to denote, we use a vertical bar in the middle to denote the probability of X given Y, right? So it means that given Y happens, right? What is the probability of the X happened? Okay. So if we realize a outcome of Y, and then what is the chance that we observe X? Okay. So in pure observation perspective, we don't do any intervention. We just observe that given that Y happened, we observe the probability that X happened, right? Which of course is observable. Right? And in intervention, we can change this formula just a little bit. Instead of saying Y equals Y, we say do Y, meaning that we are going to intervene on Y. And then we observe what is the chance of observing X, right? So in that case, we are in the world of intervention. Okay, but regardless, in both scenarios, the conditional probability is very helpful for us to understand the association. Okay, we can of course also extend that to a continuous case. Say given that Y greater than 0.5, what is the probability that X is less than 0.25 but greater than 0? Okay. And then in terms of association, we give you a very easy to understand example of buying book A versus book B. Okay, so imagine that you are in the library, you are maybe a bookstore, and the question is, what is the probability that someone will buy book A given that they bought book B, right? So then you can formalize that with the conditional probability that given book B is purchased, what is the probability of purchasing book A, right? And that is actually exactly how the recommender system works, right? Consider all the things that you bought so far from Amazon, from Shopify, from whatever shopping platform. Then the recommender system trying to predict based on your purchasing history, how likely you are going to purchase, say you have purchased a book on computer vision, then likely you are going to be recommended based on that conditional probability. You are recommended a book about natural language processing, right? So and that is usually very effective, right? Because it does actually have a higher chance of purchasing books in a similar category. But it doesn't really tell you the causality. It's hard to say because you purchased a computer vision textbook that increases your probability of purchasing a natural language processing book. Because there could be a common confounder there, right? That is common confounder, as we understand, is just, well, your passion for AI, right? And in that case, it doesn't really affect the effectiveness of the recommender system, because recommender system is built upon association, right? It won't have to review causality in order to recommend you relevant books that you have a higher probability to purchase. Right? So that is in the domain of association. And now let's introduce the idea of structural causal models, or SCMs. Okay, so the structural causal models, or SCM, is a very common way, or it is probably the most common way for us to represent some kind of causal relationship. Okay, so that is the reason why we want to learn it, because very likely, no, it hardwired to our brain, because our brain works in the way that we try to represent events in the nodes and relationship in the edges, and we try to draw some line to connect the nodes, denoting some type of causal relationship or association. Okay, so here the A and B and C, they are three separate events. Okay, and we will see that we link them with the arrow, directional arrow, denoting A causes B, B causes C, right? And A also causes C. Okay. And you may also notice that we have some nodes here, but in the dashed line, right? This denotes the exogenous nodes or exogenous events, okay, U0, U1, and U2. They are exogenous because they are not impacted by other nodes. Okay, so we would say that A and B and C, they are endogenous, meaning that they are the child nodes of other nodes. They are other nodes that causes A and B and C. Okay, whereas U0, U1, U2, they are external or exogenous because they are not impacted by other nodes. Okay, so we have the dashed line here because we basically do not observe U0, U1, U2. What we only observe is A and B and C. Okay. Okay. Any questions so far? Okay, good. Okay, and now we have some functional representation. Okay, so here we will say, how we are going to represent this SCM, the structural causal models, in using some kind of mathematical function, right? Actually, it is pretty straightforward, because here A is only a function of U0, right? But B is a function of A and U1, right? And C is function of B and U2, right? So now let's represent in mathematical function. Here we assign A to be a function. So F is a function, it's any function, doesn't really, is linear or non-linear, doesn't matter. Okay, it's a function of A and also U0. Okay, B is a function of there's the FB. Sorry, there should be, because it doesn't show this right. It should be the superscript, subscript here. So it's too big. And then it's a function of A and also U1. And then C is a function of A and B and U2, right? As you see here, C is function of B, and because B is function of A, so C is both a function of A and C is function of A and B. And also C is a function of U2, right? U2 exogenous and A and B are endogenous. Okay. So we have this kind of relationship, right? So this is how you represent the SCM using functions. Okay. Any questions so far? Good. Okay. And now we can have some actually coding exercise we can do. So let's assume that we define an SCM that can generate some data with non-zero probability of buying a book A given we bought book B, right? The conditional probability example that we give. There are many possible SCM that could generate such data, but here we choose one of them. Okay? One of the many potential function that can generate such data. Okay? Conditional probability data. Okay? So assume that we have U0, which is an exogenous variable, follow a uniform distribution from 0 to 1. And we have U1, which is another exogenous variable following a normal distribution, actually a standard normal distribution from with mean of 0 and a standard deviation of 1. Okay. And then A is a binary function when U0 is greater than 0.61. So this just means that when U0 is greater than 0.61, A takes the value of 1. Otherwise, A takes the value of 0. Okay, so that is a binary function. And B, as you see here in the causal diagram, B is a function of A, right? And also a function of U1. So therefore, we will say B would be equal to 1 if this condition holds. Okay, so if A plus 0.5 times U1 is greater than 0.2, then b equals 1. Otherwise, b equals 0. Okay, so in this case, b is a function of a and u1. Any questions so far? Okay.
Yeah, hi, I have a question.
Yeah.
Sorry if it's a silly question, but from what I understand, the structural causal models is only one direction, right? It's only unidirectional between the nodes, right?
Exactly. Yeah.
Yeah. So are there special cases that we can accommodate if the relationship could potentially be both ways, or it strictly must stick to this assumption?
Right, that's a great question. Actually, we didn't cover in this session, but it's called DAG, directed cyclic graph. So the DAG has a strict definition that is not going to be any loop. Basically, it's one directional. A causes B, B causes C, but you cannot trace C to A, right? A cannot be a cause, no, C cannot be a cause of A, because otherwise it's going to form a closed loop, linking the causation back to A, right? Which is not allowed in DAG. So there are some models that allow you to have bidirectional causation, maybe in this kind of closed loop, but it's still a very much developing area of study. So I would say probably the vast majority of the models were built upon the DAG framework, so it would not allow you to have this causal loop, tracing back the causality. But there are some models that extend that assumption so that you could actually model bidirectional causal relationship. But it's so actually I'm developing this AI causal inference course, and in the very last actually a few lectures I try to include some of those kind of modeling. But in majority of cases, it's not a bidirectional causal relationship is not allowed.
Yeah, thank you for answering my question. Yeah.
Yeah, that's a great question. Yes, because we didn't really introduce DAG. So here, I didn't mention that. Yeah, there are some implicit assumptions on the graph. Okay. But great comment. Any other questions or comment? Okay, good. Okay, so let's take a look of how we implement this idea in Colab. Okay, so let me stop share and share the Colab, so you can take a look of how we implement this conditional probability idea. So let me share the screen again. Where is my to close this and share. Okay. So in this bookstore example, I create a class. Now, for all of you who are not familiar with Python, class is the way that we create an object. Okay, so the class is more flexible than function. Now, many of you probably have learned the function. So the function have some limitations because if you create a class, you can treat this class as an object, so that you can create instances out of this class, but you can't do that with a function. So I don't want to go too much into the detail of this Python programming side, because the idea is not to talk about Python programming, but really give you some essence of the conditional probability. But here we create a class in Python. It's called book SCM. You can think about this as an extension of a function, which is more flexible and giving you direct access to the objects. So here in this function, I define a constructor. So usually if you create any, most of the classes, you would have this init function. So this is a built-in Python function. Basically here, you just define the basic parameters for your class. Okay. So here I define the random seed because I do want to replicate the starter in other settings. And then I create two random variables, U0, U1, right? You are familiar with those are the two exogenous variables. U0 causes A and U1 causes B, right? So, and then we define a method for sampling because we do want to sample data from basically purchasing books A and purchasing book B from this class. So we are going to create by default a 100 samples. And then I would say, well, if you have specified random seed, definitely use the random seed. And then here I'm going to create U0 and U1 for 100 observations. Okay, I'm going to create 100 observations for U0 and 100 observations for U1. And then follow this distribution, right? So U0 is going to be a uniform distribution. U1 is going to follow a standard normal distribution. And then I start creating these two binary variables, right? A0, as we said, is a binary variable. It takes a value of 1 if U0 is greater than 0.61. Otherwise, it will be 0. And B is a function of A and U1, right? As demonstrated in this causal diagram. So B is going to take the value of 1 if this condition hold, otherwise B is going to be 0. Okay. And then finally, I just return these two variables. Okay, so these look very similar as a function, but give you additional flexibility. So here I initialized the SCM. So SCM equals book SCM. Book SCM is the class that created. And then I can sample it, right? So I create a 100 sample from this SCM. And it creates a tuple containing both A and B, 100 observations for A and 100 observations for B. And you know that actually B is a function of A, right? And we can check the shape to make sure that they conform with our expectation. Indeed, we have 100 purchases for book A, either purchase or not purchase, 0 or 1. And also we have 100 purchase for book B. Okay, so both A and B are Boolean type data because it's take the value of 1 or true if someone purchased A, otherwise is 0 or false. Okay. So you can take a look of the first 5 elements for A and B. Okay, so this means, well, someone purchased book A, right, but not book B. Okay, so this means no purchase on book A and also no purchase on book B, right? This means no purchase on book A, but purchase on book B, etc. Right? Any questions so far? And now we are able to compute the probabilities, right? What is the probability of purchasing A? Well, that is simple because that is just the sum of A divided by the sample size of A, right? Basically, because A take only 2 values, 0 or 1, right? Therefore, you add up all the ones and then divide it by 100. And then you get the probability of buying A is about 39%. Okay. You can also compute the probability of purchase book B, and that is 0.58%. Okay. And then, well, the next question is, what is the conditional probability of purchasing book A, given that you purchase book B, right? Then you can calculate that. Calculate the conditional probability. Here I use the NP-where to do that. So where is the NP-where is from the NumPy where function. Basically, it gives you, so if this condition hold, if the first condition hold, then do this. Otherwise, do this. Okay, so that is exactly what a where function is for. Okay, so in this case, we will ask question, well, if someone purchased book B, then count the number of the book A purchase, right? And same here, the probability of purchasing book B given book A would be if someone purchased book A, calculate the number of book B purchase, right, and add them up. Okay. So if you do that, you will get the probability of buying book A given B, that is 0.638%, and the probability of buying book B given A is almost 100%, 0.95%. Okay, so this gives you an idea of the conditional probability. But then the remaining question is, now if I'm not really satisfied by the observation, I want to actually do an intervention, okay, to see what's going to happen. Okay, so if you do an intervention on an outcome variable, for example, let's go back to this idea. If you do an intervention, say here, right, instead of observing what happened to y when x equals 0, sorry, I forgot to to share the slide. So here the idea is, if I want to do an intervention, I would say, well, instead of just observing what's going to happen to y given x equals 0, I'll change x to 0. Okay, so this is intervention, and then I'll observe what's happening to y. Okay, so that is the difference between intervening and conditioning, because conditioning means we just observe what's going to happen, whereas intervening means that we are going to intervene, we are going to change the value of x and then observe y. Okay, so if we change, so first let's give some definitions. Okay, so here we would say, if A causes B, and then B would be a child of A. Okay, so and then A would be a child of A would be the parent of B. Okay, because A causes B. Okay, and then of course, if U0 causes A and A causes B, in this case we will call U0 be a grandparent, or sometimes can be a grandparent, right, of B, or in general we call it ancestors of B. Okay, so and B would be the dependents, right, of A and U0. Okay, those are the terms we are going to use. Okay, so now if consider the case that if we intervene. Okay, if we intervene on B, what's going to happen? Okay, so because A previously causes B, but then if we intervene on B, then B would be dependent only on the intervention, so that B would separate from A. Okay, so it's like a child that you raise a child in the family, right? And then suddenly for some reason maybe there's a forced enlist, right, in the army, right? And then the army person came and forcefully asked your son or daughter to be enlisted in the army, right? So that would be the intervention. In this case, the parents lost control, right? Because the parents cannot really keep the child at home because unfortunately this child has been enlisted, right? So therefore, if you intervene on B, on a child of A, and then the child would not be dependent on A anymore. Okay, so that's illustrate this case in the exercise. So let me share.
Yeah, Professor, I don't think you need to stop share and share again because two files are in the same browser.
Oh, okay. So you could see actually if I switch the
yeah, tab. I think we could see that.
Oh, okay. So that's good. Okay. Because yeah, I never know what's going to happen. So I just okay. Okay. So no, that's intervene this, right? And you can actually do this exercise yourself, right? So here, we create this intervention. Here, we create a variable 0 and 1. And then we will say, well, A, here we make things easier, right? We just say A equals U0 because A is a function of U0, and then B is a function of both A and U1, right? And then of course there's going to be a strong relationship between A and B, right? Because B is a function of A. Okay. And then that's intervene. So in this case, we set A to be a constant, okay, 1.5, and then we repeat it 100 times. Okay. And then this time B would still be a function of A. Okay. Then we can print the mean and the variance correlation. And of course, there's going to be a correlation between A and B. But now that's set A back to U0, and we intervene B so that B now is a random variable anymore. Okay, so B is not a dependent of A, B is not a function of A anymore. And then we compute the Pearson correlation coefficient again to see in this time what's going to happen between A and B. Well, actually, you can guess, right? So previously, there's going to be a strong correlation between A and B, but after we intervene B stopped to be a function of A. In this case, well, there's not going to be any correlation coefficient, right? The correlation coefficient is going to be approach 0, right? So that is the idea. So for the time being, this actually you can see probably here. So this is before we intervene. Before we intervene, there's a strong correlation between A and B, but after we intervene, the p-value is not significant, and we have almost zero correlation between A and B. Okay, and then you can do the same exercise if you intervene on A to see what's going to happen. Okay, so those are good exercise for you to practice if you want. But basically, the idea is we illustrate first how we observe, how to observe and calculate the conditional probability, and then we talk about the causal diagram, and then we talk about the idea of the difference between intervening and conditioning. Okay. Question? Okay, so let's see whether we have time to talk about the last idea. See. Okay. Okay, so let me share this again. Okay. And then a few more comments about correlation and causation. So here, no, a lot of time actually the correlation may not be depicted, as you probably all known from the biostatistics class, from the Pearson's correlation coefficient or rank correlation coefficient, because those can only identify either linear or monotonous a causal relationship, right? So if there's some nonlinearity in the causal relationship, then those matters may not be able to identify a correlation. Okay? And also sometimes if the data are truncated, it is very hard, if at all, you can identify any correlation, even if the correlation exists. So here we illustrate in two cases. First, we assign X to be follow a uniform distribution from -2 to 2, as you see here on the left-hand side. And then now Y is S squared, and then plus some error term. Okay? So you know that because X squared is polynomial term, so in this case, we have a degree 2 polynomial relationship between Y and X. So in this case, the traditional Pearson's correlation coefficient would not be able to capture this nonlinear relationship, right? But that is not the only case. So even if you have a linear relationship, but in this case, say you only observe some truncated data. For example, if you only observe the sample in the two tails, but not in the middle. So basically, if you miss the information when X is less than this is wrong, so the opposite. X is less than 1.9 is greater than minus 1.9. So basically, you only observe the two tails. In this case, well, you can later on probably run the Python file. That let me switch to that. Could you see my collab or not? Oh, okay. So that's confirmed that Yu is right. Okay. So in this case, first we create some X as a random variable following a uniform distribution, and then we square that, and X squared plus some error term is going to be Y. In this case, you observe, of course, observe a polynomial quadratic term between x and y. If you calculate the correlation coefficient, well, it's going to be very small, right? And the p-value is not significant, meaning that the Pearson's correlation coefficient doesn't really capture this nonlinear relationship between x and y. And if you just get rid of the middle, okay, you only observe the two tails. And what's going to happen? So in this case, you only observe a small range of x, which is very close to -2 and 2. In this case, if you run a correlation coefficient, well, it's almost 0, right? So you really can't really detect anything if your data is highly truncated, right? Okay, so the final thing I want to, oops, I probably, oh, it's here. Okay. Can you see I transitioned back to Sway?
Yes.
Okay, great. So the final thing that is I want to say is about the counterfactual, right? We don't have much time, so let's do this exercise. This is I would say a very interesting exercise. So the question is, what is the probability that some people similar to you react to coffee the way you reacted, given similar circumstances, right? If you are doing an intervention, you are trying to understand what would happen if you say drink the coffee and then you feel bad in your stomach, right? So is the coffee really affect your stomach? What would happen if you did not drink that coffee, right? Would you still feel painful on your stomach or not, right? So if you run an experiment, of course, you can answer a similar question, right? What's the probability that some people similar to you are going to react to coffee, right? But not exactly you, right? The reason is the experiment is not done on you, and also you don't know the counterfactual, right? If you really want to answer the causal question, you should ask it differently. Maybe here I listed, given an alternative role that is identical to ours and only differed in the fact that you did not drink the coffee this morning, plus the necessary consequence of not drinking it, what is the probability that you feel bad in your stomach, right? So this is the counterfactual question you may ask if you really want to dig into the causal relationship, right? But fundamentally, of course, you would not be able to answer this question, right? So the second best choice is to do a randomized experiment. But then you know one is cannot be generalized to yourself, and second, it doesn't really hold everything the same, right? Because besides the people who are different, the other situations have also changed, right? It is not exactly holding everything constant. Okay, so here in the hypothetical case, actually you could estimate the counterfactual, right? The counterfactual question is this one. So this one I feel it's not easy to understand, but it's fascinating to look at this formula. Okay, so here x here the y denotes whether you feel terrible in your stomach or not. Okay, and then y equals 1 means you feel terrible in your stomach. Y equals 0 means you do not. Okay, and x1 means you drink the coffee in the morning, and x equals 0 means you did not drink the coffee in the morning. Okay, so the conditional probability can be specified in the counterfactual pattern in terms of given that you drink the coffee in the morning, okay, and also given that after drinking coffee, you feel terrible in your stomach, okay, in the afternoon. What is the probability, the counterfactual probability that you still feel painful of your stomach in the afternoon without drinking the coffee in the morning? Okay, I don't know to what extent that makes sense to you, but that is the counterfactual. Okay, So it asks directly the counterfactual question. If you want to list that into your conditional problem, it looks something like this. Okay, so here actually I give you explanations of all that. Okay, in greater detail. So you will say, well, this is not possible, right? No, we would never be able to observe the counterfactual world. But actually, the Pro actually provide a way to computing the counterfactual, of course, given some assumptions, right? So his way of computing the counterfactual follows 3 steps. The first step is abduction. Abduction means using evidence to calculate the values of the exogenous variables. Here, the exogenous variable is the sensitivity of your stomach, right? Because if your stomach is not sensitive to coffee, then it doesn't matter whether you drink coffee or not. You don't feel anything, right? But if you have a sensitivity to the coffee drinking, then you probably have a problem, right? So therefore, the abduction phase is to calculate, using the available evidence, calculate your sensitivity, which is an intrinsic value to coffee drinking. Okay? And the second is modification phase, where you replace the structural equation for the treatment with a counterfactual value. Right? So basically, you got the counterfactual value from the abduction, and then you replace that into a structural equation. And the third is when, because you have modified the structural equation, then you can use that to make a prediction. Okay, so those are the 3 steps illustrated by Pro to compute the counterfactual. Okay, so using his idea, so we create this very simple, of course, hypothetical scenario. Okay. So here we say, well, U is our exogenous variable. U equals 1, standard coffee sensitivity. U equals 0, standard no coffee sensitivity. Okay, and now we need to assume that there is an exact equation denoting the causal mechanism for reaction to coffee, and this equation is shown here. Okay, so T here we denote the T means T equals 1 means no drink the coffee, T equals 0 means not drinking the coffee, right, in the morning. And then the Y, the outcome, which is whether you feel terrible of your stomach, equals this equation. So T times U plus T minus 1 times U minus 1. Okay. So T only take 2 values, either 0 or 1. Drink the coffee or not, right? And U here is also a binary variable, right? 1 means you are sensitive to coffee. U means 0 means you are not sensitive to coffee. Okay. So if we assume the structural equation, the causal mechanism is exactly this, and then actually magically we can calculate your U, your value of U, basically sensitive to coffee or not, based on this equation. Okay, so this is because you already know that when T equals 1, when you drink the coffee in the morning, you had a terrible stomach ache, right? So you know actually when T equals 1, Y equals 1, right? Because that is what you observe in the factual. Okay, so if you know this, and then you can replace this formula. So first you can rearrange this formula. Okay, rearrange this formula so that U would be equals to this. Okay, U would be equal to a function of T and Y. Okay, and this is super easy, right? So this is just primary school or middle school math, right? You will rearrange U to the other side so that U become a function of T and Y. And then, well, because you know that when T equals 1, Y equals 1, and then you replace that value, you assign the value for T and Y so that you can calculate U, right? Not surprisingly, if T equals 1, Y equals 1, and then U equals 1. Okay, now actually you solved your unique value of U, and U equals 1 means, well, unfortunately, you are coffee sensitive. Okay. And then when you know that you are coffee sensitive, of course you can put it back, right? You are done with the abduction stage because you've solved the exogenous variable. And then in the modification case, well, you just need to insert your solved value for U as well as the new treatment status with a 0 means that you did not drink the coffee in the morning, right, into the equation, right? So therefore, when you have U, t equals 0, do not drink coffee in the morning, and then replace also U with 1 here, you will solve for Y, right? And then you can use that to make a prediction, right? And then, well, if you replace U with 1 and T with 0, and you solve for Y, and then Y actually equals 0, means that if you did not drink the coffee in the morning, you would not have a stomach ache. Okay, is that something magic? Okay, of course, this is based on strong assumption that you have first exogenous variable, right? And you have no other unknowns, right? You can fully specify your here outcome variable, based on the exogenous variable and the treatment status, right? In this case, actually, you can solve and make prediction on the counterfactual. Okay. Any question?
Yeah, how we get Y equals to T times U and this formula? I mean, just
you mean this one?
Yeah.
Yeah. So this is assumption, right? Because you have to assume this is the utility function, or this is the causal mechanism, right? And of course, in reality, you seldom know that, unless probably in the physical process, right? You would tell that, well, no, I don't know, for precipitation is a function of snow melting and something else, right? So in social science, in health, you seldom know this function, right? But if you know for sure that this function is the causal mechanism, then you can solve for it. Okay. So this is completely hypothetical, right? Of course, in reality, seldom you even know this is the case, right? Yeah. Other question? Okay, so that's hopefully you learned something for today's session. And well, I apologize. This is really the last minute of my preparation for the presentation, because I was just notified couldn't make it today. So I would encourage you to study more about AI causality, and I would recommend this. Actually, most of the materials are come from a book that I'll recommend you to take a look if you're interested. I'll in the chat box. Oh, actually, I'll send that to Yu so she can share that with you later on. So if you're interested in AI causality, this is a huge field that denotes a lot of investigations and a lot of opportunities. So myself have been doing causal inferences for a long time, starting with my doctoral degree, doctoral study. But really recently, I started to pay attention to AI causal inference, which opened new doors, new ways to causal inference modeling and discovery. So I would encourage you, if you have the appetite or interested, definitely explore this field. This field could be exploded over the next few years. Like the NLP models and computer vision models that blossomed recently, you're probably going to see the AI causality field to be the next wave of AI. Of course, no one can force the future, but no, this field is definitely denotes a lot of attention. Okay, so that's all for today, and Yu is going to send you some learning materials, and that's keep our passion about learning AI. And in 2 weeks, Fan is going to deliver her talk on Metaflow, which is a popular platform, open sourced about Meta to do a lot of end-to-end machine and deep learning tasks. Great to see everyone. Take care. Bye.
Thank you.
Thank you.
Thank you. Bye.
Thank you.
Bye.
Thank you.